Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on Building Energy Systems and Auditing. Today we are in the module number 2. Module number 2 we are discussing on the topic of building energy systems, and today is the 10th lecture where we will discuss the low energy cooling systems. In the last lecture, in the lecture number 9, we have discussed the earth air tube, and this lecture we will be covering two important part of the low energy cooling systems. One is the radiant cooling systems and another one is the passive downdraft evaporative cooling system. So, the radiant cooling system is basically a kind of a system where through floats or maybe sometimes in the wall panel the kind of the chilled water is going to flow, and that will radiate the heat and try to radiate in the inside the building, inside the space, and that space cooling going to happen. So, there are two type of radiant cooling. One is called the chilled slab, because if the roof slab or just below the roof slab, in between the roof slab and the ceiling, false ceiling or the suspended ceiling, if this it hosts some kind of pipelines and those pipelines are filled with flow of chilled water. The similar kind of the chilling panel is also can be provided, which is a part of the wall or maybe the full wall, where through the chilled water will passes through the wall system itself, and definitely that wall must be the external wall, because that will going to take the maximum amount of heat gain, and that will be taken care of. That particular heat gain will be nullified by this particular flow of water. So, the room is going to be cooled, or in other sense we may say that the cooled air flow will chill the panel, chill the slab, and from there the radiation will actually take care of the total temperature drop of a particular space. So, in this slide I have shown a particular chilled air system where the basically it represent a slab which are having some kind of pipelines, and this is definitely passes through the whole surface area of the slab, and this particular pipelines will filled with the flow of the water, chilled water. Temperature may be around 8 degrees centigrade, 10 degrees centigrade or so. So, by passing through, and if there is a kind of a fan over there or something like a kind of a downdraft kind of a thing is there. So, a descending air will actually be cooled, and that can be comes from the ceiling, or sometimes it can be also implemented in the walls. So, it comes from the wall. So, that is the concept over this particular type of the radiant cooling systems also. So, by virtue of this particular process, the chilled air, when it is returned back to the plant, so I have shown that one is red color dotted line, this one, it will be little bit hotter. So, by virtue of the thermal exchange, it will be little bit hotter, because it is passing through the surface which is a hot surface. It is become the hot surface become cool. So, where that particular heat will go, it will go to it will raise the temperature of this cooled air, the chilled air, water also. So, the how I can now those are the basic principles. Now, let me understand how this particular behavior or this particular system behavior can be mathematically modeled. So, there are two things happening simultaneously. One is the heat is going to be absorbed by this cooling system or the radiant cooling systems. What is this radiant cooling system? It is the chilled air water which is going to passing through this particular embedded mechanism of the slab, or maybe below that, anyone can be implemented. So, this heat will be absorbed by this the radiant cooling system. So, if it is absorbed, somebody has to lose the heat. So, which part of the system is losing the heat? It is nothing but the room, the whole air in the room is actually going to losing the heat. So, I have represented this, the heat absorbed by the cooling system by capital Q, whereas the heat loss by the room is maybe by capital H, and these must be equal with a kind of efficiency mark or whatever factor, efficiency factor. This heat balance must be equal. So, let us see how to compute this Q and how to compute this H. So, Q can be computed as A into V. What is A? A is a diameter area of the pipe, and V is the flow or the velocity of the water that passing through this particular chilled the pipe. The rho W is the density of the water, S water is the specific heat of the water, and T out and T in are the outlet temperature and the inlet temperature. As because by virtue of the heat exchange, this outlet temperature will be definitely going to be higher. So, suppose there is a chill panel kind of a thing. So, if you are sending some 8° temperature, definitely this will come out with a maybe 18° temperature or so. So, this is going to be your T out and this is your T in. So, the difference is delta is your 10° centigrade or so. So, now if I see this is A is your meter square, always I love to do the unit balance. So, that can give me some kind of a confidence that these two sides are equal and what will be the units of the final unit. So, V is your meter per second, this is multiplied by the rho is your kg per meter cube into this is your joule per kg per degree C multiplied by this is degree C. Okay. So, this is your meter cube. So, I will do it over here itself, this is meter cube get cancelled, kg also kg gets cancelled, degree C, and so it is left with joule per second, which is your watt, right. So, this much is your total heat gain through this system of the, because of this chilled water is passing through and there is a temperature difference. But the next H, how should I compute H? H can be computed. What is H? H is the heat lost or by this particular air inside a particular space. So, how much is the volume of the room? VR. The VR is the volume of the room. And what is S air? S air is the specific volumetric specific heat of the air. So, how much joule temperature is required to increase 1° temperature of 1 meter cube of the air or whatever. So, again if I do this particular the unit balance, this V is in your meter cube multiplied by this joule per meter cube and this temperature is your degree C. So, finally, I will come out with joule, not joule per second here. So, that is the total amount of the energy that will be taken out by the room. Now, you see there will be equilibrium condition. So, somebody is passing through and taking out some kind of heat and somebody is losing the heat. At certain time after this will be a steady state. Initially there will be very high amount of energy loss and then gradually it will reduce down and there is a time will come which is I called as a steady state time or whatever will be reached after t second, such a way that the total loss is equal to will be the total gain or whatever, and then there will be thereafter there will be no change if there is no certain change of the change in some temperature or so. So, if you change the temperature of the inlet water, definitely things will be going to change or whatever, but otherwise it will remain as constant. Suppose this constant equilibrium state or the steady state will take t second time after you start any kind of a flow or so. So, this Q into T, Q was in joule per second, multiplied some second with some factor of eta, because there will be definitely some kind of a losses or so, there is some kind of efficiency factor. So, that I must be equal to H, then this will be, this H is in joule. So, both the sides, the right hand side and the left hand side, the unit will be going to balance. So, finally, my equation, mathematical modeling equation, mathematical modeling on the radiant cooling will be Q into capital T into eta, efficiency factor must be equal to the heat that is going to lose by particular space, and the H and Q can be computed by virtue of these two equations. So, again let us solve a small problem. So, a data has been given that it is for a radiant cooling systems, the velocity of the pipe through the pipe is 0.3 meter per second, the diameter of the pipe is 75 millimeter. So, definitely I can find out the A, and this is the V is already there. I know the inlet temperature and the outlet temperature is 12 degree and 22 degree C. In the previous case we discussed that as a 8 degree and 18 degree, something like that. We know the room dimension, we know the initial temperature of the room, how much, 40 degree, and that will definitely going to be cooled down because it has to lose some kind of a heat by virtue of this system. The T, capital T is this, 10 minute time is the capital T, efficiency is 50% and work done by this cooling is 45 degrees. So, what I have to find out is that what will be the final room temperature after steady state. So, definitely that temperature will be much less than 40 degree, but I have to find out that what should be the temperature, and also I have to find out the COP, coefficient of performance. So, I have found out this particular Q by virtue of that equation that we have discussed. This is my area, I found out area, V is already given, rho and S is I know that one, this the specific heat and the density of water, inlet temperature and the outlet temperature. So, if I give everything over here, so I got as a 55.5 kilowatt joule per second or kilojoule per second is the total Q or the heat flow that will be taken away from the room to the pipes water. Similarly, I have to find out now H. So, the equation is this equation where I know the room volume is 1000 meter cube, the volumetric specific heat of air I know the initial temperature, but I do not know the final temperature. So, that will be the unknown in this equation. So, I put the V, I put the S of the air, I put this to the temperature, and finally, it has to be something like 1250 multiplied by 40 minus T kilojoule. If you remember, this heat H that comes out from the room will come in joule or kilojoule or megajoule, whatever may be, but the Q is in the form of watt, kilowatt or something like that. So, I have to multiply with time. So, that time is also given to me as 10 minute, which is equal to 600 second, and 50% is the efficiency. So, I will go back to the third formula where Q is 55.5, this Q is 55.5, T is 600 second, eta, that is the efficiency factor is 0.5, and the total H is there, and I have only unknown is T. So, by solving I got T is 26.68 degree, which is far below that 40 degree. Now, I know that this particular system works well. So, that means if I run the system with this 12 degree temperature and whatever maybe this flow velocities and whatever the cross section diameter of the pipe, definitely is going to be help me, my temperature will be going down from 40 degree to 27 degree or something like that. But whether it is beneficial, so I have to check with the COP, the coefficient of performance. It has to be more than 1, otherwise I do not want to employ this system, because I have to work, there should be some kind of a work, and that work should give me some kind of benefit. So, the COP I have found out the Q, that is your 55.5, whereas 45 kilowatt is your total the expenditure by virtue of running, that I have mentioned over here. The 45 kilowatt is the work done for the cooling. So, that is your W. So, by virtue of some kind of a cooling arrangement, we have to cool the water or so. So, you may use some portion evaporative cooling, then maybe some kind of the other type of cooling, and then you have to some kind of refrigeration cycle it has to be passed through. So, total 45 watt is going to be your total amount of the energy expenditure by run this cooling system, and you have to use pumps also, and you are your total heat heat loss is about your, if I go back little bit, 55.5 kilowatt is your total that heat you are getting taken out from the room. So, that is your benefit. So, this is your benefit, this is your expenditure, which is slightly above 1. So, we may decide that whether I can go with these systems or no, or sometimes I want to reduce this 45 to little bit less. So, I can get better value of the COP. 1.23 is definitely acceptable, but may not be we can go because it is not that much of high value. The earlier exercise in the last class, we have whatever we seen last lecture, that is almost like 6. Anything like 3 and around is very much appreciated. So, next we will discuss the passive downdraft evaporative cooling system. This is a purely evaporative cooling systems, and in this particular systems is used for long time in some of the desert areas. If you go to the some of the areas like the Arabian countries or so, this particular systems is used widely. So, the system is something like, if I want to see this is a kind of a cooling tower, and this system is called also as a PDEC, the passive downdraft, because it is downdraft from top to bottom. I will take the water in, the air in, and I have to cool it. So, here you see in the top part of this kind of shaft, it is a shaft kind of a thing. There are some buffle walls, and there are some outlets or the punchers. So, those punchers actually take care of the hot air, hot outside air in. I have shown in red color arrows, and this buffle wall will try to channelize that towards the towards below. Please remember that the hot air is lighter. So, it always want to go upward in direction. So, this buffle wall will be such a way has to be designed, and there will be some kind of the mechanism of some kind of a pump, downdraft pump, fan, not pump, will be there. So, that will actually take that particular hot air in to that particular the shaft. The next level is, this is the entry level. The next level, you see there are some kind of the wall and some kind of the systems has to be adopted, where the water sprinkler systems has to be there. So, water will sprinkle from top to bottom, or probably from bottom to top and bottom, so something like that, and that will provide such a way that whenever the air flow towards the down, it should pass through this wet the water wall or the surfaces. So, there may be of some kind of a honeycomb kind of a surfaces, which is always going to be wet by some kind of a water sprinkler, and through that water this honeycomb kind of a surfaces, air is actually passing through, and movement of the air is should be through that particular holes and pores, and it will going down, and maybe there is another fan below which again downdraft that one a bit. So, if you remember, if you imagine that this very slowly this hot air is passing through this particular honeycomb kind of structure, which is wet by water, it will take care of the moisture from the wet wall or the honeycomb structure, and it will cool down by virtue of the evaporative cooling. And by virtue of this particular evaporative cooling system, whenever it come to the third layer, again there are some kind of a buffle wall that will going to deliver this cooled air or the after evaporative treatment, the cooled air to the different levels or so. So, you see now this is the blue color arrows, that means cool air, which was hot in the first layer, now it is cooled through the second layer, and now it is channelized to the different level, upper floors and lower floors or so. So, this is the total mechanism, and maybe in the last you can have some kind of a pit where you can actually get some kind of water, because some water definitely going to fall down, and you have to collect that, and again you have to recycle that to the up. Of course, the water temperature will be little high, you have to again make it little bit cooler. So, by this is the downdraft, passive downdraft evaporative cooling systems. It can be only applicable where the evaporative systems is applicable, that means in the climatic zone like hot and dry climate. Particularly in the desert climate, it will be very good to provide, and it will be very efficient in those kind of desert climate. You will get very high value of COP over there, and you will get very cool kind of air, and that will be definitely going to help the indoors. So, again let us see from the mathematical modeling, because mathematical modeling, simple mathematical modeling is always important, because you need to see that whether if I add up, see we have seen the last one, the COP value is something like 1.23, which is more than 1, but not so much good with respect to our whole soul expenditure or so. So, we have to see that how much is actually our benefit, how much I can cool down. There I am going to cool down from 40 degree to 26 degree, which is good enough, but the COP value may not be that much good. So, I have to see here also what mathematical modeling I can propose for this particular the PDEC system. So, again we have to see the two parts, somebody is losing some kind of a heat and something is some gaining. So, this heat losing of the heat or heat lost and the heat gain should be the proper balance, that should proper balance with each other. So, how much heat will be lost by the air is I have written in this equation. So, HL is the Q of air. What is Q? Is a flow rate, how much meter cube per second air coming from at this particular inlet level, and the S air is your volumetric specific heat, Ti and To is the what is your inlet temperature and what is your outlet temperature. But here the inlet temperature will be higher than the outlet temperature, because by virtue of this process it will lose some kind of a heat. So, that is why this Ti minus To is written out. Now, this particular the heat loss by the air should actually somebody has absorbed. Who has absorbed? The heat actually absorbed by the water. So, the heat absorbed HA by the water is nothing but the EA. EA is rate of evaporation multiplied by the latent heat of absorption. That was how much is absorbed. Rate of evaporation, the how much rate, what is the how much per second, how much rate it is evaporated. So, how much is water is now evaporated, water was in a liquid state, and after 1 second how much water from the liquid it become vapor. So, that is the rate of evaporation, and by virtue of multiplying with the latent heat, which is 2260 kilojoule per kg of water, if I multiply that I can find out, yes, this much amount of heat is actually absorbed by the water, and that water become a vapor, percentage or that particular amount of is become the vapor. So, this EA, first we need to find out the EA, sorry not EA, ER. ER is the rate of evaporation. The rate of evaporation can be found out by the difference between these two ratio HRO and HRI. The humidity ratio of the inlet the outside humidity ratio of the outlet and the inlet. O stands for outlet and the R. So, there is a here at least at this particular is the outlet HRO, and at this point maybe it is your HR inlet. So, there is a difference. So, humidity ratio has a, I am just writing this wrong, this will be HR inlet, this is HR outlet. So, definitely this will be high, this will be very high, this will be low. So, from this high to low, the difference of the humidity ratio multiplied by the Q of air, that is the flow of the air, and multiplied by rho of air, or so density of air or so. So, by virtue of this I can find out the what is the evaporative the rate, and I can use that with the latent heat and I can equate that one. So, again a small numerical problem at the last we can solve. So, in a passive downdraft evaporative cooling systems, I have following data. The cross section area of the inlet is 0.5 meter square and the velocity of the air is 0.25 meter per second. So, I can find out this Q air by virtue of that. And then I also know the temperature of outdoor air is 38 degree, humidity ratio in the outdoor air is 6 and humidity ratio at the indoor air is 14 gram per water per kg. So, find out the outflow temperature. So, I have used this equation. So, I know that this is the rate of the airflow by multiplying this the velocity and the cross section area. Cross section area is 0.5 meter square and velocity is this your 0.25 meter per second. So, again let me write down this Q is nothing but a Q of air is nothing but your area multiplied by the velocity, right. This is so that gives me 0.125 meter cube per second. So, that is there multiplied by the SV, SV is your the 1250 joule per meter cube. So, again let me do the unit balance, this is meter cube per second I got, and then I multiplied with the specific volumetric specific heat joule per meter cube degree C, and this delta T is in degree C. So, very similarly I got the value of joule per second, which is what. So, that much what, but here this term is still yet to be found out, that is how much is your treated air temperature. I have taken the air from the inlet as 38 degree, what will be after this passive cooling, how much is the temperature I have to find out. So, now let us the other part of it, heat absorbed. I know the humidity ratio in and out, I think it was something it was 6 gram to 14 gram per kg. So, this is 6 minus 14 divided by 1000. So, that is the kg to that becomes the kg from gram to kg multiplied with the inlet air flow, that is 0.125 and this is the 1.225 is the density of the air. So, that means 1.225 into 10 to the power minus 3, this much is your kg of water per second is evaporative rate, right. So, because this is your the change of the evaporation, that much water changes, that much particular water from 14 to 6 is the change of the water content, moisture content of the air, and this moisture content of the air is applicable on a flow of 1.125 meter cube per second with some density. So, that means this much 1.225 10 to the power minus 3 kg of water per second is evaporated out, right. So, that is your ER. So, 1.225 into 10 to the power minus 3 multiplied by this 2260 is the latent heat of the air, and what is this 1000 is actually going to be transferred that to from kg kilojoule to joule, and so that's this much of what is your total amount of the heat absorbed by the air by virtue of the evaporative cooling. So, I have both the things ready, HL and the HA, just equating that I can get the T outlet is your 20.3 degree, which was 38 degree in the beginning in the inlet side, 38 degree to 20.3 degree centigrade or so. So, these are the some of the examples of the low energy cooling systems in India. There are some books on it. So, you can visit those books and know about these particular systems more. So, what we understand is that in the conclusion we must say that the radiant cooling systems and the passive downdraft evaporative cooling systems are two very efficient method of low energy cooling systems also, but definitely we have to look into that, where should I go, should I adopt this particular thing, what is the COP value and all. So, the radiant cooling systems is work based on the sensible heat loss or gain, sometimes if you send some kind of the hot water, and whereas the PDES system is the purely evaporative cooling systems. Thank you very much.